Okay, so I've been learning about Pythagoras, and the dirt on him is just too good. You've probably heard of the Pythagorean theorem, but not the part where Pythagoras was a crazy cult leader who thought he'd made a deal with a god thousands of years ago and could remember all of his past lives. Oh, and he killed a guy. I mean, maybe it was a long time ago. And he was afraid of beans. As in beans, they just, freaked him out or something, I don't know. But mostly I want to talk about the murdery part. See, Pythagoras and his cult of Pythagoreans had this cool kids club where they'd talk about proportions all day. They'd be like, hey, I drew a 2x3 rectangle using a straightedge compass. Isn't that awesome? And then someone would be like, hey guys, I have a box that's 2x3.5. And the cool kids would be like, 3.5? That's not a number. Get out of our club. And then they'd make the units half the length and call it 4x7, and everything was okay. Even if your box is 2.718 by 6.28, you could just divide your units into thousandths, and you'd get a box that's a nice, even 2,718 by 6,280. It's not a simple proportion, but hey, the box still has a whole number proportion, so Pythagoras is happy. Unless it's a box of beans, then he freaks out. I like to imagine what it would be like to think of numbers the way they did. Maybe you think of numbers as being on a line. Numbers one way, then zero and negative numbers the other, and there are numbers between the numbers, fractions, irrationals, filling in the gaps. But Pythagoras didn't think about numbers like this at all. They weren't points in a continuum, they were each their own separate being. Which is still pretty modern, because before that people only thought of numbers as adjectives, numbers of. In Pythagoras' world, there is no number between 7 and 8, and there isn't a number 3/2 so much as a relationship between 3 and 2, a proportion. 6-4 has the same relationship, because the numbers share this evenness, which, when accounted for, makes it 3-2. The universe, to Pythagoras, was made up of these relationships. Mathematics wasn't numbers. Mathematics was between the numbers. But while people admire how much Pythagoras loved proportions, there's a dark flip side to that obsession. How far was he willing to go to protect the proportions he loved? Would he kill for them? Would he die for them? And the answer was he'd go pretty far until beans got involved. It's time for timeline time. Mathematicians like lines. I want the context, because in school today, if you bring out the ruler and compass and are like, let's do some geometry, let's draw two lines at 90-degree angles using a straightedge and compass, here's a happy square, then you've probably had years of math class already and think of geometry as being harder than adding big numbers together. You probably think that zero is a simple, easy concept and have heard of decimals too. Well, here's now, 2012. Here's Einstein, Euler, Newton, and Da Vinci. That sure was a while ago. Now let's go all the way back to when Arabic numerals were invented and brought to the West by Fibonacci. Before that, arithmetic was nightmarishly hard, so if you can multiply multi-digit numbers together, you can go back in time and impress the beans out of Pythagoras. And before that, there was no concept of zero, except in India, where zero was discovered around here. And if you keep going back, you get to year 1. There's no year 0, of course, because zero hadn't been invented. And back a bit more, you get to folk like Aristotle, Euclid, Archimedes, and then finally, Pythagoras, all the way back in 6th century BCE. Point is, you can do some pretty cool mathematics without having a good handle on arithmetic, and people did for a long time. And in school, when they tell you you need to memorize your multiplication table and graph a parabola before you can learn real mathematics, they are lying to you. In Pythagoras' time, there were no variables, no equations or formulas like we see today. Pythagoras' theorem wasn't a squared plus b squared equals c squared. It was the squares of the legs of a right triangle have the same area as the square of a hypotenuse. All written out, and when he said square, he meant square. One leg's square, plus the other leg's square equals hypotenuse's square. 3 literally squared plus 4 made it into a square. Those two squares have the same area as a 5x5 square. You can cut out the 9 squares here and the 16 here, and fit them together where these 25 squares are, and in the same way, you can cut out the 25 hypotenuse squares and fit them into the 2 leg squares. Pythagoras thought you could do this trick with any right triangle, that it was just a matter of figuring out how many pieces to cut each side into. There was a relationship between the length of one side and the length of another, and he wanted to find it on this map. But the trouble began with the simplest right triangle, when where both the legs are the same length, when where both leg squares are equal. If the legs are both 1, then the hypotenuse is something that, when squared, gives 2. So what's the square root of 2, and how do we make it into a whole number ratio? Square root 2 is very close to 1.4, which would be a whole number ratio of 10 to 14, but 10 squared plus 10 squared is definitely not 14 squared, and a ratio of 1,000 to 1,414 is even closer, and a ratio of 100 million to 141,421,356 is very close indeed, but still not exact. So what is it? Pythagoras wanted to find the perfect ratio he knew must exist, but meanwhile, someone from his very own Pythagorean brotherhood proved there was no ratio. The square root of 2 was irrational, that in decimal notation, once decimal notation was invented, the digits go on forever. Usually, this proof is given algebraically, something like this, which is pretty simple and beautiful if you know algebra, but the Pythagoreans didn't. So I'd like to imagine how they thought of this proof. No algebra required. Okay, so Pythagoras is all like, there's totally a ratio. You can make this with whole numbers. And this guy's like, is not, is to, is not, is to. Fine, have it your way. So there's a whole number ratio in simplest form where this square plus this square equals this square. Yeah, that's the Pythagorean theorem. I made it. Yeah, though for this triangle, you don't even need the full theorem. It's easy to see that it's the same area by cutting each part into 4 triangles. But I don't want to divide the squares up into triangles. I want unit squares. So you mean kind of like this, where this square is divided into units, and so is this one, and they all fit perfectly into this one, and vice versa, but not like this. It almost works, but you start dividing the square evenly to fill out the 2 equal other squares, and you got this one odd one out. There's an odd number of squares to begin with, so you can't divide them evenly between the 2 squares. There's not even a right triangle. What's your point? Just that you know an odd number like 7 isn't going to be it, without even trying. An odd number times itself gives an odd number of squares. So whatever this number is, it can't be 7. It has to be even. Okay, so the hypotenuse is even. That's fine. So what if I prove the leg is even too? Then it's not in simplest form. Any ratio where both are even, you divide by 2 until you can't divide anymore because one of them is odd, and then that ratio is the best. I thought we assumed we were talking about the simplest form ratio. We are. If there's a ratio in simplest form, at least one of the numbers is odd, and since the hypotenuse has to literally be divisible by 2, then the leg must be the odd one. So what if I proved the leg had to be even? You just proved it's not. It can't be both. Unless it doesn't exist. What you forget, Pythagoras, is that if this is a square, then the 2 sides are the same. Just as this is divisible right down the center, so too is it divisible the other way. And the number of squares on this side, which are the number of squares in just one leg, is an even number. And for a number of squares to be even, what does the number have to be, Pythagoras, oh my brother? If leg squared is even, then the leg is even, but it can't be even because it's already odd. Unless it doesn't exist. But if they're both even, you could divide both by 2 and start again. But this still has to be even, which means this still has to be even, which means you can divide it by 2 again, but then it has to be even, so everything is even forever, and you never find the perfect ratio. Oh, beans. He had a vision, a beautiful vision of a world made up of relationships between numbers. If this wasn't a whole number ratio, then what was it? The Pythagoreans still believed, wanted to believe, that irrationality was somehow false and the world was as they wanted it, so this proof stayed secret, until someone spilled the beans. According to some, it was all a guy named Hippasus, and Pythagoras threw him off a boat to drown him as punishment for ruining what had been perfect. Or maybe it was someone else who discovered it, or Hippasus, or someone else who was killed by the Pythagoreans long after Pythagoras was dead, or maybe they just got exiled, who knows. And how did Pythagoras die? According to one guy, some guys got mad because they didn't get into the cool kids club. So they set Pythagoras' house on fire, and Pythagoras was running away, and they were chasing him, but then he came upon a field, and not just any field, but a field of beans. And Pythagoras turned around to face his pursuers and proclaimed, "Better to be slaughtered by enemies than to trample on beans." And he was. Others say he ran off and starved himself to death, or just got caught by his enemies because he ran around the bean field instead of through it, or who knows what happened. People claim Pythagoras didn't like beans because he thought they were bad for digestion, or gave you bad dreams, or reminded him of male genitalia, or because he didn't want a clubhouse full of flatulating mathematicians, or he just didn't like them metaphorically. He and his followers were or weren't vegetarians, did or didn't sacrifice animals, possibly were only allowed to eat certain colors of birds. I mean, he definitely had a lot of rules to follow, but just what they were and what they meant is lost to history. I'd like to give you a colorful story about exactly what happened with Pythagoras, but somehow that kind of truth doesn't last. What I do know is that the square root of 2 is irrational, that there's no way to have the length of a side of a square and of the square's diagonal both be whole numbers. Mathematical truth is truth that endures. This proof is just as good now as it was 2,500 years ago. I mean, it's awesome, and it shows that there's more to the world than whole numbers, and shame on the Pythagoreans who didn't have the beans to admit it.